Yes, we expect James Webb to make great discoveries. Like quantum physics and general relativity, and you'd come up with some bigger understanding, deeper understanding. String theorists have been all into this. You get a multiverse.
Do multiverses exist? Could our universe be just one among many? The concept of a multiverse, popularized in movies like Everything, Everywhere, All at Once, where parallel universes are explored, may seem far-fetched, but it has piqued the interest of cosmologists who are striving to understand if multiple universes coexist and whether they could potentially support life. Excitingly, the James Webb Telescope has recently provided intriguing insights that suggest the possibility of a multiverse or parallel universe. This remarkable discovery has sparked immense interest and is challenging long-held theories. The profound impact of this finding has stirred up curiosity and controversy, particularly regarding the nature and characteristics of such a multiverse. So, in this video, we will delve into this mind-bending concept and explore how the James Webb Telescope has provided insights into the possibility of a multiverse. Picture yourself embarking on a remarkable journey aboard a rocket, venturing far beyond Earth's boundaries. You soar past the outer reaches of our solar system and even leave behind our entire galaxy. Breaking through the cosmic confines of the observable universe, you encounter the awe-inspiring expansion of the unknown, ignoring the fact that surpassing the speed of light is currently impossible, but let's indulge our imagination. As you traverse through this unimaginable void for countless eons, a stunning revelation awaits you. A new universe unfolds before your eyes. Within it resides another galaxy, complete with its own solar system and even another Earth. And there, sitting in front of a screen, you behold another version of yourself watching this very video. This mind-boggling scenario represents the concept of the multiverse, a notion that arises naturally from the physical theories that attempt to explain the origins of our universe. According to cosmologists, when our universe was incredibly young, it underwent a period of rapid expansion known as inflation. In a minuscule fraction of a second, the universe expanded to an immense size, although the exact magnitude remains uncertain and highly speculative. Most inflation models propose a universe at least 10 to the power of 52 times larger than the observable cosmos, which itself spans an enormous 90 billion light-years. This vastness is almost beyond comprehension. Inflation solves many problems in standard Big Bang cosmology, a model that describes how the universe began, such as the fact that regions of the universe far apart have roughly the same temperature. According to inflation theory, before inflation ripped them apart, those regions were much cozier and got to know each other quite well. Another potential consequence of inflation is that it may not be done. It may never be done. This is known as eternal inflation, and it describes how on the grandest scales, the universe may always be inflating, with only tiny pockets pinching off to become normal, sedate patches like our own. Each snatched-off island universe would be separated by a vast chasm of nothingness, with the islands flying apart faster than light, as inflation does. These island universes, which are embedded within the larger multiverse, would never meet and could never communicate with one another. So, could we, in the absence of direct evidence, make an educated guess as to whether the multiverse is likely or not? That is where the James Webb Space Telescope comes in. The JWST has made an exciting discovery recently, uncovering 6 massive ancient galaxies that defy scientists' expectations. These galaxies formed when the universe was in its infancy, at a mere 3% of its current age. What makes these galaxies truly remarkable is their size, exceeding what was believed possible for galaxies that emerged so soon after the Big Bang. If the findings are confirmed, it would require a re-evaluation of our understanding of how the earliest galaxies came into existence. Dubbed universe breakers by astronomer Joel Leya, they challenged the prevailing notion of small, young galaxies during this period and instead reveal galaxies as mature as our own, defying conventional wisdom. This discovery is mind-boggling as it highlights the vast gaps in our knowledge about the universe and the formation of galaxies. It's akin to stumbling upon an unexpected twist in a puzzle that fundamentally alters our understanding. Another intriguing aspect detected by the keen eyes of the James Webb Telescope involves peculiar fuzzy dots observed in the images. These dots appear unusually bright and exhibit a striking red colour, which holds immense significance in cosmology. In astronomy, the redness of celestial objects can indicate their age. As light travels through the expanding universe, it undergoes stretching, resulting in a redshift. The presence of these fuzzy dots suggests the existence of galaxies that formed approximately 13.5 billion years ago, a mere 500 to 700 million years after the Big Bang. Scientists are astounded by their discovery, as it challenges previous assumptions about the early universe, akin to uncovering ancient cosmic treasures that defy our expectations. While these galaxies may not be the oldest observed by the James Webb Telescope, their size is what makes them significant. These fuzzy dots hold an astonishing amount of mass, potentially hosting billions to hundreds of billions of stars comparable to the Sun. It's like witnessing the birth of colossal galaxies that rival the grandeur of our own Milky Way. These remarkable findings have left scientists with much to contemplate, even causing some uneasiness among them. The presence of such massive galaxies at such an early stage of the universe challenges fundamental concepts in cosmology and our understanding of the formation of the first galaxies. It's akin to discovering a puzzle piece that doesn't fit with the rest, prompting a reconsideration of the entire narrative of early galaxy formation. According to our current understanding, after a period of rapid expansion, the universe cooled down, allowing gas to come together and form the first stars and galaxies during the Dark Ages when there was minimal light. However, these unexpected discoveries disrupt what we thought we knew about this crucial epoch in the universe's history. It's like uncovering a new puzzle piece that contradicts our previous assumptions. Scientists now face the task of delving deeper, gathering more data, and developing new theories to make sense of these extraordinary findings. They are like cosmic detectives, unraveling the secrets of the early universe in a captivating mystery. These groundbreaking discoveries have reignited interest in a long-standing question: does the multiverse truly exist? The initial phase involves investigating the concept of inflation. While its validity is still being debated, there are indications that something resembling inflation occurred in the early universe. The pattern of fluctuations observed in the cosmic microwave background, which is the light emitted when the universe started to cool around 380,000 years after its formation, aligns with what one would expect from inflation. No other theory of the early universe can account for this pattern of light. This alignment is a positive indication. However, it's important to note that inflation encompasses a range of theories rather than a singular explanation. It represents a class or category of theories that differ in their underlying physics, causes and effects, and driving mechanisms of this event. Since these theories are based on hypothetical models of the extreme physics of the early universe, it is still premature to determine which, if any, of these theories are accurate. Physicists speculate that eternal inflation is a common outcome, inherent to most, if not all, inflationary models. Based on this hypothesis, if inflation is indeed valid, then eternal inflation would likely hold true, suggesting the potential existence of a multiverse. Undoubtedly, accepting the existence of the multiverse presents a considerable challenge. If eternal inflation is accurate, it implies not just multiple universes or a vast number of universes, but an infinite collection of pocket universes. Each of these universes could potentially possess its own distinct laws of physics and arrangements of particles. If the possible ways to arrange matter and energy are finite, meaning there is a limit to the combinations that can form a universe, then an infinite multiverse necessitates the repetition of identical physical situations, even if specific configurations are incredibly rare. That means there's a copy of you at some finite but very far distance away, and another copy past that, and another. Countless iterations of you engaging in the same activities would exist throughout this infinity of parallel universes. However, asserting the likelihood of the multiverse is contingent on internal inflation becoming a common occurrence. A recent paper by a team of physicists, published on the preprint database ArXiv and submitted to the Journal of Cosmology and Astroparticle Physics, explores numerous inflation models, considering variations in the types of models and their parameters. The researchers examine which models result in a singular occurrence and which models lead to eternal inflation and the formation of a multiverse. And their answer? It's complicated. Initially, the researchers discovered that eternal inflation is not as widespread as previously believed. It turns out that earlier cosmologists had limited their studies to a specific set of models, which led them to assume that eternal inflation was a common occurrence. However, upon exploring a broader range of inflation models, the researchers found that many viable models, ones that did not contradict observations, did not result in an eternal inflation scenario. Nonetheless, the researchers encountered difficulties in accurately determining the commonality of eternal inflation. This challenge arises from our incomplete understanding of inflation models and their underlying mechanisms. They emphasized that it is challenging to provide a definitive measure of genericness for eternal inflation because there is still much to learn about the physics of inflation. Given the current state of knowledge, it is not possible to provide a single answer to the question, and further exploration and understanding of inflation are necessary. So, is there another you out there watching this exact same video? Science says it's tough to say. What are your thoughts on the possibility of multiple versions of yourself existing? Is there a chance that there are numerous iterations of you out there? Share your opinions in the comments section.